Dear students, today we will discuss about the metal oxide semiconductor field effect transistor and also that is MOSFET. So what is the MOSFET? A metal oxide semiconductor field effect transistor MOSFET. MOSFET is a field effect transistor where the voltage determines the conductivity of the device. The ability to change conductivity with the amount of applied voltage can be used for amplifying or switching electronic signals. MOSFET are now even more common than BJT, bipolar junction transistor, in digital and analog circuit. So this is the diagram of the MOSFET structures in which three terminals are there: source, drain, and gates, and also the one p-type substrate here. So this is the simple MOSFET structure. Next one is the type of MOSFET. So generally MOSFET are two types. One is N-channel enhancement MOSFET or N-MOSFET, and second one is P-channel enhancement mode MOSFET or P-MOSFET, and N-channel depletion mode MOSFET, and second one is the P-channel depletion mode or P-MOSFET. So there are basically two type of MOSFET: enhancement type MOSFET and depletion type MOSFET. That is the structure of the MOSFET, metal oxide semiconductor field effect transistor device. Typically in this diagram, the typically length L equal to 0.03 micrometer to 1 micrometer and width equal to 0.05 micrometer to 100 micrometer, and the thickness of the oxide layer is in the range of 1 to 10 nano ampere. So this is the dimensions of the MOSFET for the structures, and there are different p-type substrate body and N channel here, and drain region also, and oxide layer SiO2 perspective view of the in MOSFET structure, and in cross section of the MOSFET structure. So there is three terminal: source, gate, and drain, and also a oxide layers, that is the SiO2, and a thickness of the this layer is kept very minimum, and also there is a channel region which have the length of L, and also a p-type substrate here that is we have as a body, and so there is total four terminals in MOSFET device. One is source, second one is gate, third one is drain, and fourth one is substrate, that is the body or body terminal. Next one is the MOSFET operation. Operation with zero gate voltage. So with zero voltage applied to the gate of the MOSFET, two back-to-back diodes exist in series between drain and source in MOSFET. So N plus drain region and P-type substrate, and P-type substrate and N plus source region. These back-to-back diodes prevent current conduction from drain to source, and when a voltage VDS is applied, the path between drain and source has a very high resistance or of the order of 10 to the power 12 ohm. And next one, channel for current flow in the operation of MOSFET. So in this diagram, the source and drain are grounded and applied a positive voltage to the gate, that is the BGS. The BGS repels the free holes from the region of the substrate under the gate, the channel region, and these holes are pushed downward into the substrate, leaving behind a carrier depletion region. And positive BGS attract electrons from the N plus source and drain regions into the channel region. So when a sufficient number of electrons accumulate near the surface of the substrate under the gate, and N region is in effect created connection the source and drain regions. That is the in this diagram of the MOSFET operation. Now next, if a voltage is applied between drain and source in this circuit diagram, current flow through this induced and regions. The induced and region thus form a channel for current flow from drain to source, and this is called an N-channel MOSFET or an N-MOSFET transistors. The channel is created by inverting the substrate surface from P-type to N-type. Hence, the induced channel is also called an inversion layers. So, the excess of BGS over VT is termed the effective voltage of the overdrive voltage and is the quantity that determines the charge in the channels. So, here BGS minus Vt equal to V naught V. Note here N-channel MOSFET is formed in a P-type substrate in this diagram. Gate and channels region of the MOSFET form a parallel plate capacitor with the oxide layer acting as the capacitor dielectric. Positive gate voltage causes a positive charge to accumulate on the top plate of the capacitor, the gate electrode. Negative charge on the bottom plate is formed by the electron in the induced channels. So this field controls the amount of charge in the channel. Hence, it determines the channel conductivity when a voltage VDS is applied or voltage drain to source applied. This is the origin of the name field effect transistors, FET. In this diagram, we apply a small signal VDS. The voltage VDS causes a current ID, that is the drain current, to flow through the N channels. So current is carried by free electrons drain. An N-MOSFET transistor, in that case, VGS is greater than the device act as a resistance and especially the channel's conductance is proportional to the BGS minus BT, and thus ID is the proportional to BGS minus BT into BDS. Now, applying a small BDS, the ID minus BDS characteristics of the MOSFET. So these are the characteristics of the MOSFET between drain current versus drain to source voltage is the different BGS gate to source voltage. So when the voltage applied between drain and source BDS is kept small, the device operates as a linear resistance whose value is controlled by the voltage between gate to source. So in this VI characteristics of MOSFET, there are different value of VGS, and this is the graph between ID versus VDS. In MOSFET operation of the enhancement and MOS transistor, as VDS is increased, the induced channels acquire a tapered shape and its resistance increase as VDS is increased. Here BGS is kept constant at a value greater than VT, or BGS equal to VT plus V naught B. So drain current ID versus BDS for an enhancement type NMOS transistor operated with BGS equal to VT plus V naught B. So this is the operation structure of MOSFET by the diagram, and also we can explain this with the help of VI characteristics of the MOSFET, in which VI characteristics in this characteristics or graph curve bends because the channel resistance increase with BDS, and also current and voltage. Here the in this graph there is a saturation region in which BDS is greater than V naught B here. So, and in this diagrams, these are two diagrams of MOSFET P channels. There is a physical structure of PMOS transistor in diagram first and diagram second. There also here a n-type substrate and PMOS transistor, and also there is a induced P channels and different gate current and source current and drain current also across the different terminals. So the circuit symbols for n-channel enhancement type MOSFET, and this is the first symbol for the n-channel enhancement type MOSFET in this symbolic diagram, and second one is the modify symbol for the n-channel MOSFET, and third one is the simplified circuit symbol for the MOSFET. Here is the circuit diagram for the ID versus BDS characteristics. So We apply the here voltage between gate and source, and also in outside we applied the DC voltage VDS voltage drain to source, and in this circuit diagram we draw the VI characteristics of MOSFET between ID versus VDS. So there is different value of ID and VDS. So at the point where the current is saturated, in that case VDS greater than V O naught and VGS equal to will be BTN plus B naught B, or in this cutoff region VGS less than BTN. So here is a slope. So GDS equal to 1 upon RDS and equal to K N dash W upon L into V naught B. So this is the also a triode region where VDS less than V naught B, and so this is the ID versus VDS characteristics of the MOSFET. Here is also circuit diagram for the MOSFET operation and the VI characteristics between the ID versus VDS. Then ID VDS characteristics for an enhancement type of NMOS transistor in this diagram, and VI characteristics of the MOSFET. Next topic is biasing in MOS circuit. So what is the role of biasing and what types of biasing in the MOSFET circuit generally used, and biasing in MOS amplifier circuits. So an essential step in the design of a MOSFET amplifier circuit is the establishment of an appropriate DC operating point for the transistor. This step is also known as biasing or bias design. An appropriate DC operating point on bias point is characterized by a stable and predictable DC drain current ID and by a DC drain to source voltage VDS that ensure operation in the saturation region for all expected input signal levels. So there are different types of biasing here in MOSFET amplifiers. So first biasing by the fixing BGS, second biasing by fixing BGS, BG and connecting a resistance in the source. Third one is biasing using a drain to gate feedback resistor, and next one is the biasing using a constant current source. So these are the different types of biasing which is generally used in MOSFET amplified circuits. So first one is biasing by a fixing BGS. The most common approach to biasing a MOSFET is to fix its gate to source voltage VGS to the value required to provide the desired ID. So this voltage is derived from the power supply voltage VDD through the use of an appropriate voltage divider. The independent of how the voltage VGS may be generated. So this is not a good approach to biasing a MOSFET, because we know that the drain current ID equal to 1 upon 2 mu n COX W upon L into VGS minus VT का whole square, and the threshold voltage V naught of the oxide capacitance COX and transistor aspect ratio W upon L vary widely among device of same size and type. So in biasing by fixing VGS is not a good technique. In this figure, two VD, ID versus VGS characteristics are representing extreme value in batch of MOSFET of the same type. And for the fixed value of VGS, the resultant spread in the values of the drain current can be substantial. Next one is the biasing by fixing BG and connecting a resistance in the source. And this biasing is as shown in this circuit diagram. So an excellent biasing technique for discrete MOSFET circuit consists of fixing the DC voltage at the gate VG and connecting a resistance in the source lead as shown in the figure. So we can write from the figure the VG gate voltage equal to VGS plus RS ID, and where VGS is the voltage between gate to source and RS is the source resistance and ID is the drain current. And if VG is more greater than VGS, in that case ID will be determined by the values of VG and RS. If VG is greater than VGS, then resistor RS provided negative feedback, which will stabilize the value of the bias current ID. From equation, when ID increase and VG is constant, so VGS will decrease, which will further decrease ID. Thus, the RS work to keep ID as a constant as possible, and this negative feedback action of RS gives it the name degeneration resistance. So VGS equal to here VG equal to VGS plus RS ID. And in this figure, show the ID versus VGS characteristics for two devices that represent the extreme of a batch of MOSFET. A straight line that represents the constant imposed by the bias current, namely in this figure, the intersection of this straight line with the ID VGS characteristics curve provides the coordinates ID and VGS of the bias point. And also in this case, the variable obtained in ID is much smaller. Also note that the variability decrease as VG and RS are made larger. And next, by fixing VG and connecting a resistance in the source. So practical implementation using a single supply. In this circuit diagram, the utilize one power supply VD and drives VG through a voltage divider RG1 and RG2 resistance. That is the voltage divider resistance. Since IG gate current equal to 0 and RG1 and RG2 can be selected to be very large in the M range, allowing the MOSFET to present a large input resistance to a signal source. Next one is biasing using a drain to gate feedback resistor. In this circuit diagram, a simple and effective biasing arrangement utilizing a feedback resistor connected between the drain and the gate as shown in this figure. And here the large feedback resistance Rg, usually in the mega ohm range, force the DC voltage at the gate to be equal to that at the drain terminal because Ig equal to 0. Thus we can write voltage gate to source equal to voltage drain to source equal to VDD minus RD ID, which can be rewritten in the form VDD equal to VGS plus RD ID. And if ID increase due to any reasons, then VGS must decrease. And the decrease in VGS in turn cause a decrease in ID, drain current. So thus the negative feedback or degeneration provided by the RG works to keep the value of ID as constant as possible. Next biasing is biasing using a constant current source. The most effective scheme for biasing a MOSFET amplifier is that using a constant current source as shown in this figure. And here Rg usually in mega ohm range, and establish a DC ground at the gate and present a large resistance to an input signal source that can be capacitively coupled to the gate. Here resistor RD establish an appropriate DC voltage at the drain to allow for the required output signal swing while ensuring that the transistor always remains in the saturation region. So this is the biasing using constant current sources. So we had discussed the different type of biasing for the MOSFET device. Next one topic is the small signal operation model for the MOSFET device. So in small signal operation and models for the MOSFET device, we consider the conceptual amplifier circuit as shown in this figure. In this figure, conceptual circuit to study the operation of the MOSFET as a small signal amplifier. Here the MOS transistor is biased by applying a DC voltage VGS and the input signal to be amplified, and VGS is superimposed on the DC bias voltage VGS. So the output voltage is taken at the drain in this figure. DC bias point in this small signal operation model of MOSFET, the DC bias current ID can be found by setting the signal VGS to 0. Thus, ID equal to 1 upon 2 Kn into VGS minus VT का whole square and also equal to 1 upon 2 Kn V naught V square. Here it is assumed that lambda equal to 0. Here V naught V equal to VGS minus VT is the overdrive voltage at which the MOSFET is biased to operate. So overdrive voltage is that at which the MOSFET is biased to operate. The DC voltage at the drain, so VDS will be equal to VDD minus RD ID, where VDD is the DC voltage supply across the drain terminal and RD is the resistance across the drain terminal and ID also flow the current into the drain terminal here. So to ensure saturation region operation, we have must VDS greater than V naught V. Furthermore, since the total voltage at the drain will have a signal component superimposed on VDS and VDS has to be sufficiently greater than V naught V to allow for the required negative signal swing. Next, what is the signal current in the drain terminal? So we consider the situation with the input signal VGS applied here in this figure. The total instantaneous gate to source voltage will be VGS equal to VGS plus VGS from this circuit diagram. The resulting in a total instantaneous drain current ID will be equal to 1 upon 2 Kn into VGS plus B small VGS minus BT the whole square and also 1 upon 2 Kn VGS minus BT the whole square plus Kn into VGS minus BT into small VGS plus 1 upon 2 Kn small VGS square. So 1 upon 2 Kn VGS minus VT the whole square DC bias current ID and 1 upon 2 Kn VGS square represent the non-linear distortion and Kn into VGS minus VT into VGS current component that is directly proportional to the input signal VGS. To reduce the non-linear distortion induced by the MOSFET, the input signal should be kept small so that 1 upon 2 Kn VGS square is very less than Kn V into VGS minus VT into VGS, resulting in VGS is very small 2 into VGS minus VT or equivalent VGS is very less than 2 V naught V. If this small signal condition is satisfied, then ID can be expressed as drain current equal to small ID equal to ID plus small id and also where small id equal to Kn into VGS minus VT into VGS. The parameters that relate ID and VGS is the MOSFET transconductance Gn. So transconductance of the MOSFET Gn will be equal to ID upon VGS or equal to Kn into VGS minus VT. On in term of the overdrive voltage VOB voltage overdrive and transconductance Gm equal to Kn B naught B in term of voltage drive voltage. This figure show the small signal operation of the MOSFET amplifiers. So in this figure show a graphical interpretation of the small signal operation of the MOSFET amplifier. Note that Gm is equal to the slope of the ID VGS characteristics at the bias point. So here transconductance Gm equal to change in ID upon change in Bs when VGS is constant. So what is the voltage gain? So for the MOSFET, the total instantaneous drain voltage VDS as follow. VDS equal to VDD minus RD ID. Under the small signal condition, we have VDS equal to VDD minus RD into ID plus small id, which can be written as VDS equal to VDS minus RD small id. So thus the signal component of the drain voltage is VDS equal to minus ID RD or equal to minus GM VGS RD, which indicate that the voltage gain is given by AB, that is the voltage gain equal to small VDS upon VGS or equal to minus GM RD. The minus sign indicate here that the output signal VDS is 180 degree out of phase with respect to the input signal VGS. So this is the figure of the conceptual circuit to study of the operation of MOSFET. In voltage gain, the input signal is assumed to have a triangular waveform with a amplitude much smaller than 2 into VGS minus VT. The small signal condition to ensure linear operation. For operation in the saturation active region at all time, the minimum value of VDS should not fall below the corresponding value of VGS by more than VT. So the maximum value of VDS should be smaller than VDD. Otherwise, the FET will enter the cutoff region and the peaks of the output signal waveform will be clipped off in that case. So in this figure, the conceptual circuit to study of operation of MOSFET, and second figure, the total instantaneous voltage VGS and VDS, that is represented by the different waveforms between VGS per set time. Next, small signal equivalent circuit models of the MOSFET. So the FET we have as a voltage control current source. It accepts a signal VGS between gate and source and provide a current GM VGS at the drain terminal. The input resistance of this control source is very high, ideally infinite or in the range of mega ohm. The output resistance is also high in this case. In this figure, in figure first, neglecting the dependence of ID on BDS in the active region, what in second figure, including the effect of channel length modulation modeled by output resistance are not equal to VA into ID. So these are the two figures of small signal models for the MOSFET. So in small signal equivalent circuit models, in this analysis of the MOSFET amplifier circuit, the transistor can be replaced by the equivalent circuit model as shown in figure. The rest of the circuit remains unchanged except that ideal constant DC voltage source are replaced by the circuit. And most serious shortcoming of this model is that it assumes the drain current in saturation to be independent of the drain voltage, but actual drain current depends on the VDS voltage across drain to source in a linear manner. So such dependence bar modeled by a finite resistance R node between drain and source. So first figure show the neglecting the dependence of ID on VDS in the active region. So this is the small signal equivalent circuit. And second one is also small signal equivalent circuit model for the including the effect of channels length and modulation. So for this topic, there are two reference books. One is Integrated Electronics by the Bellman and Alkas, and second one is the Electronics Device and Circuit by Millman and Alkas. There are some multi-choice question here. So question first is the depletion and channel MOSFET. Option A can be operated as a JFET with zero gate voltage. Option B can be operated as an enhancement MOSFET by applying positive bias to gate. Option C can be operated as an enhancement MOSFET by applying negative bias to gate. Option D cannot be operated as the enhancement MOSFET. So here correct answer is option B. The depletion and channel MOSFET can be operated as an enhancement MOSFET by applying positive bias to gate. Next question, MOSFET has greatest application in digital circuit due to option A, less power consumption, option B, less noise, option C, small amount of space in place on a chip, and option D, of the A1. So here correct option is answer A, that is the MOSFET has greatest application in digital circuit due to the low power consumption. In next question, the enhancement and channel MOSFET, option A cannot be operated as an enhancement MOSFET. Option B can be operated as a JFET with a zero gate voltage. Option C can be operated as an enhancement MOSFET by applying negative bias to gate, and can be operated an enhancement MOSFET by applying positive bias to gate. So here correct option is A. So here correct answer A, that is the enhancement and channel MOSFET cannot be operated as an enhancement MOSFET. So these are also some multi-choice questions. Thank you. Thank you very much.